So what I'm going to talk about is some general cartography. And this is essentially the list of things that are kind of my pet peeves that I see people do wrong over and over again in maps, or I see the questions that they're not asking about their data. And so I thought this would be a nice opportunity to highlight some of them and kind of help you keep them in mind as you're finishing up your hacking projects this week, if it involves making any actual maps. I will give you the disclaimer that I primarily work with vector data, so I do not have brilliant thoughts on how to symbolize your rasters. So my general goal when I talk about cartography is this idea that people are really good at making sense of spatial patterns, and that if you design your map well, it's going to help people find those spatial patterns faster, more efficiently. They're going to feel more comfortable that they've gotten the right answer. But there's kind of some problems that come up along the way, so I'm going to talk about those problems. And where I come from on this is, I think with any map you make, there are these really these two axes that you need to be really, really careful with. One of them is what you've heard a lot about over the last few days, which is thinking about the quality of data representation. Are you using the right data set? Have you done the right analyses on it? Have you created the right nuggets of information to even put onto your map? Are you using the right level of measurement? You know, kind of all of the technical nuts and bolts into going to make a good spatial visualization. The other axis is thinking about the quality of design. So is your mom going to hang this on the fridge because it's awesome looking? Or is your mom going to be like, cool, thanks. Is the ink compostable? So the goal is to get you to that stage of the data is good enough and the design is good enough. You know, this may not be National Geographic, but it's totally understandable to people, and mom will put it on the fridge. And when you hit that sweet spot, you get to the point where you're really helping people understand the spatial data, understand the spatial pattern that you're trying to communicate. When you don't do that, let's say you've got a really, really beautiful like National Geographic map, but your data really sucks. You get your sea dragon of misleading but believable, because whether we like it or not, if it looks pretty, people trust it. And if you have, you know, really low quality design but like the best data set ever, no one's going to believe it because, you know, it's ugly. It went in the compost. So I'm going to hopefully try and get you some tips to make those better maps so you avoid the sea dragons, and to help you take advantage of this cartographic license that I'm now bestowing upon all of you. And I do have this as an Illustrator format, so I can print cartographic licenses should anybody need them. The UCSB members probably actually recognize Dr. Map on here. It's Keith Clark. He's a professor at Santa Barbara. I'll just totally out him as his secret identity, Dr. Map. So the important thing is cartographic license. It's a license to practice the art and the science of cartography. It's not going to provide any protection from any form of cartographic distortion or from the misuse of cartographic products. So it's pretty all-encompassing, but it comes with some caveats. So you've got, since I'm granting all of this to you, you now have the freedom to adjust map content, layout, appearance, and level of distortion. So you get to pick your map projection. Just don't pick the wrong one, because I'm going to find you. You can choose between bad data and no data. And I'm guessing in all of your projects, you've probably already started to make decisions about that. We need to get to X, but here's the data set we have. So now what can we do? And then you get this great thing that comes in really when you do cartography, which is you get to create new truths as needed. You get to add stuff, delete stuff, move stuff, re-represent things in order to tell a specific story. And that carries some pretty significant weight when it comes to thinking about whether you're doing the right thing when you're making maps. So just some examples, since we're talking about cartographic license. These are some things that you really shouldn't do. And we'll start with the bad examples. Anybody want to take a stab at this one?
Switzerland.
Yeah, not Switzerland. Good that CNN was on top of that. I really like this one. A student made this for me custom. She said, I'm trying to do as many bad things as I can in one map. And I totally appreciated it. It was really funny when I asked her, so what happened to Idaho? And she said, oops, because she didn't realize that she had accidentally deleted it when she made this beautiful specimen. This is one of my favorite that's a little bit more recent. So I tried really, really hard to come up with why this wasn't wrong. And this is the best that I could come up with by doing all sorts of searches in Brazil for Hong Kong. So now you've seen some bad examples, and I'm going to show you some probably marginally better examples, some of which will still actually be bad examples, but we'll talk about why they're bad. And we'll talk about some rules to think about as you're making maps. So the first thing is always make sure you're using the right visualization. You're making a map. The map is the right visualization, sorta. So why should you be making maps? Well, one reason is because maps are really pretty. These are some examples from John Nelson, who works at Esri. I think he makes some really, really beautiful maps. And like 99.9% of them are totally useful, and I really like them. You might make a map because you have spatial data. You know, it has latitude and longitude. I should totally put that on a map. You make maps because you're all in a Geohackweek, and you can make maps. So you should totally make maps. Yeah, so those are all like totally the wrong reasons. I don't know why these, there we go. Totally the wrong reasons to make maps. You make a map because it's going to help you answer a spatial question. If you don't have a spatial question before you start making your map, you're probably not going to make a map that really has an answer that somebody's going to be able to get. So just some examples of that. Which county has the highest adult obesity rate? So at Tableau, you know, we make it easy for people to make maps. They love to be like, oh, I totally have county names. I'm going to throw all my data on a map. It's going to be awesome because it's spatial. And then I'll say, what question are you trying to answer? Well, I want to see where the highest values are. Great. Where is the highest value? Anyone? How would you go about finding the highest value on a map like this? We got tooltips. There are only 3,000 counties. It'd be awesome. So that's not the right visualization. So always make sure that the question that you're asking is really going to be answered by that map. In this case, the map is not a great reason, or not a great way of answering this question. You just want to make a quick chart, make a bar chart, and say, hey, now I can sort them, and I know which one's the highest value. My question is answered. Link the chart to the map if you really need people to be able to pull out the spatial location. You're going to use the map because you have questions like, where are the regions with highest obesity rates? Are there spatial clusters? How does it change across space? And once you get into that level of question, then you're going to be, you know, really using a map for what it's good for. Or you could make things like this, which probably got tweeted a lot. I grabbed it off of somebody's, you know, Twitter feed. Gross domestic product of major powers in 1939. We've got proportional symbols, we've got a couple colors, we've got our allied powers, we've got our axis powers. It really doesn't answer any question for me other than it's a map and people like maps and people will tweet maps. I could totally answer questions by maybe making a pie chart that shows me the difference in the total. Or by breaking it into a bar chart. I mean, there's so many other ways of answering the question that the map doesn't get at. So don't do that. Next thing, make sure you're using the right symbols and the right encoding. So this is saying, use the right colors. Use size for things that are quantitative. Use shape for things that are qualitative, where you want to see differences between categories. Why do you care about this? I know this map is a little bit old, but I just love it so much that I'm going to keep using it. So it's domestic freshwater use for 1990, and there is a legend, and I want you guys to tell me which color is the highest value. Okay, which color is the lowest value?
Blue. Red.
It's either blue or red or green. You guys are really good at this game. So here's our answer. Blue is the lowest, red is the highest, greens and yellows and blues are somewhere in the middle. You can actually logic it out pretty well. Texas and California, why would they potentially use more water than other places? Agriculture, there's something bigger though. Population, yeah, they happen to have a lot of people, and it turns out that people like water. So if you just use the right symbolization, if I showed you this map first and said, which state uses the most water? Probably the dark blue one. Not only is it using blue, which people are associating with water, it's using this light to dark color scheme where people normally associate light with less stuff and dark with more stuff. Unless you like to use the fancy dark colored base maps, in which case you want to flip that, because it's all about the contrast against the base map. So if you really like a dark color base map, make your high values light and your lower values darker. So I'm not going to dig into symbolization a whole lot, but I'll give you a couple questions to ask yourself. What level of measurement is your data? Do you have categories and nominal data? Do you have ordered categories of interval level data or ordinal data? Do you have interval or ratio, which are numeric data sets? If you don't know about levels of measurement, Google Stevens level of measurement. It's an important thing to know with any data analysis. What type of data do you have? Points, lines, or polygons, or rasters? Is there anything special about your data? The values are continuous. The values are discrete. I need to show deviation from a central point, so I've got a diverging data set. I want to use special symbols that people are going to understand. Men's room, women's room. If you can answer these questions, then I put my little GTS acronym on there. You guys know what that means? Google that and you can fill in the S. I've also just given you some references because I'm not going to spend a lot of time talking about this particular problem, but these are 4 things that I think will be really useful for answering questions. One is a more academic-y paper on visual variables. So those are the symbols that we put on maps. There's a chapter that somebody scanned from the Slocum textbook, Cartography and Geovisualization. No comment on any copyright issues, but somebody else had already done it, so I'm just pointing you to their website. And I'm going to give Anthony a copy of the slides, so you'll have these links. There's a really nice pocket-sized book called Cartography and Introduction. It's like 13 pounds from the British Cartographic Society. It's a super straightforward, great reference. And my personal favorite, Color Brewer, because I'm a cartographer and everybody's like, so what color should I make this? I'm like, I don't know, go to Color Brewer. It's the best way to just get somebody to tell you what colors are actually going to look nice and are going to work on your projector and everything else. So next thing is always think about your underlying data and what your map is really showing. So let's go back to our water map and how useless it is. So we know that big states tend to have more people tend to use more water. What question are we really answering with this map? We're answering the how many people live there question. Does it have anything to do with water? No. So why did I make this map? To tell you where people live? Not a whole lot of reason. So it really just comes down to you're making a population map. And it's really funny watching how slow it is sometimes watching these slides change, because you're going to get a really good comic in just a second. OK. I knew if I just waited for it long enough, you would get this. So this is the big geographer pet peeve. We've got our site's users. We've got subscribers to Martha Stewart Living. We've got consumers of furry pornography. Totally see the relationships between these. Yeah, and if these were all counts, they're really just all population maps. Your comparisons, not super valid. Or the next map that comes up, I'll just start talking about it. The National Park Service did this really cool project to look at the areas where there was more sound pollution. So it's the picture of America's cacophony of sounds. They use, I took this quote, it's like, they exploit computer algorithms in this ambitious project. And I think it's really cool, and I really like the map. And what the map really tells me is that it's louder where there are more people. And I love that they had a fancy computer algorithm that told them this, so they could make it as a cool map. I also kind of wish I did it, because it's really neat. So I always ask the question of what might actually be influencing your data, especially when you're using anything that looks like a count. You generally want to turn that into some kind of ratio. You want to take out those characteristics that you could say, oh, this is just a population map, or oh, this is just because you can do more things in a bigger area, or oh, this is just because there are more women there or more men there. Figure out what the influencing variables might be and then get rid of them. So if I take the water withdrawal data and say how many people live in each of these states, I get a new map, the water withdrawals per capita. And that tells me something that's a little bit more interesting. So I can say, hey, what's going on in Utah? They're using more water than I would expect for a region of that population. Okay, it also happens to be kind of arid, and there are probably other There are other reasons that we could dig out, but it at least gives us something we can latch onto and start asking some interesting questions. So you also need to think about what your symbols mean and what people might interpret when they see them. And that's where data classification comes in really handy. A lot of the work that you guys have done in the last few days, as I've been watching with raster data, has used these equal interval classifications. And generally that is great for that kind of data. You know, you're working with elevation, you're working with temperatures, you're working with things that you're going to put in a raster. You're not going to have like, okay, the lowest color is going to be like 12 to 17 degrees, and then the next color is going to be 17 to 106 degrees. And no, that's stupid. It makes sense. People think about, okay, 10 feet, 10 feet, 10 feet, 10 feet. You want to think really carefully about how you're breaking these continuous data sets down into little chunked color schemes. So I've given you 3 maps to show what happens with the same data set. So the top map is using a continuous color ramp. Take the low value, take the high value, interpolate the color in between, magic, done. The next one is showing equal interval. Take the low value, take the high value, break it up into even chunks on the number line. The third map on the bottom is showing a 5-class quantile. So each one of those bands of numbers is about 20% of all of the counties in this data set. Visually, what is the pattern? If I were going to use one of these, and these are showing percent of children under the age of 18 living in poverty. If I were going to use one of these to say, I need more money for school lunch programs, which map do I use? Dark stuff is more, light stuff is less. Which map tells me I need school lunch money? The one on the bottom. Yeah, there's a lot of area that's really dark. That means there's more stuff there. This is a problem. So now if I'm the person with the money bags that says, I have nothing, I'm giving you nothing, which map do I counter with? Probably one of the top 2, which says, you know, there are like 3 counties that have problems, so go away. How many people are going to read the legend on most maps that you make? Like maybe 3 of you, and you guys are people in this room who care about doing stuff with geodata. And you still are probably not really going to look at the legend other than to confirm less stuff, more stuff. Blue means water. Yep. Don't assume that people are going to spend a lot of time caring what you put in the legend. So think carefully about what those class breaks mean. If you know your data set, I would recommend not using one of the out-of-the-box classification schemes when you're creating things like choropleth maps. Think about what the values are in your data set and what kind of meaning you can pull out of them that will help people understand the point that you're trying to make with the map. So here I've taken that same data set, I've used a diverging color scheme broken on the national average, but I've also labeled the national average. So if anybody is really looking at this legend, they're not just like, oh, okay, so from 3.4% to 24.57, they're like the gray blues. Cool. No, this tells you the reason those are broken there is because those are things below the national average and everything else is above the average. So you really quickly can pull out above, below, high, low. You've got another dimension that you can interpret this data on. You can also exploit that with the color scheme. So instead of using something like a diverging color scheme, what if I really, really want to show one particular class? So this is taking that percent of population under 18 in poverty data set and saying, I really want you to pay a lot of attention to this highest class. I've made those red. They're more visible than everything else, but all of the other classes now have this light to dark color scheme so you can still see how everything compares. You got a lot of things to choose from. So these are the QGIS out-of-the-box options. You got equal intervals, just break things up along a number line. You've got quantiles, give me roughly equal numbers of enumeration units in each grouping. Natural breaks, which is, I think, the most overused and misleading classification scheme. I know none of you would do this, but if you were using ArcGIS, it is also the default classification scheme. And when I was teaching cartography classes, students would turn in their labs and I'd be like, okay, let's talk about your class breaks. So what class breaks did you use? You know, using nice professor voice. And they're like, oh, well, so it's the 5-class natural breaks. Like, super. So why'd you choose that? Because it's wrong. And they're like, because that's what it said, it was optimal and good. No, it's not optimal, it's not good. I mean, from a statistical standpoint, it can be optimal if you know why you're using it. It's minimizing variation within a class and maximizing variation between classes, but it's probably not going to give you class breaks that make sense for your data set. So if you actually know your data set, which I hope you do, think about, do I want equal intervals? Do I want something like quantiles because I really need to see top third, bottom third, middle third? Do I want standard deviations because I want people to be able to pull out where's the mean and show me how far away from the mean are these values? Think about what the question is and then figure out the class breaks that are going to help you see the answer to that question faster. It's also important when you're making maps to make sure you have just enough context. So this is kind of the blinging up the background, because it's not just the data that you put on top, but it's about people being able to do something useful with it. So here would be my default cool Tableau. I had some latitude and longitude. I'll drop them on the map. Great! What are these points on a map? Huh. If I add in a little bit of context, so just throwing the roads on there, all of a sudden you can start to see what this pattern is, because it's going to give people this visual, I guess, I don't know what the equivalent of a visual handhold is, a little eyeball hold, so that you see the data in enough context to make sense of what the pattern is. Or even fancier, I'm a huge Mapbox fan, and I love the pirate base map. I think it's good for just about everything. And as you zoom in, it's just got the greatest fonts. It's really nice. Also, don't be afraid to just get rid of the base map altogether. If you're working in online mapping systems, they often want to just give you, hey, here are all the Google streets. Here's this fancy set of tiles that we've made for you. Sometimes the data can really speak for itself just fine, especially when you're working with familiar shaped regions. You need to know the limitations of your map. So you guys talked about map projections this morning, so here's your 30-second refresher. Earth, roundish. Map, flattish. In order to go between the two of them, magical math happens. But think of it as, I'm just taking the skin of my Earth and I'm just like unpeeling it and I'm squishing it down onto my piece of paper. And in order to turn it into something that looks a little bit nicer than like a torn up orange peel, I've got to start stretching it and warping it and altering all of those nice spatial relationships on the globe. And that's going to impact the maps that you make a whole lot. You're probably going to hear about 4 general categories of map projections. So even if you don't know the technical name of the projection you're looking for, oftentimes they might have one of these words in them. You might see conformal, and conformal means that it preserves local angles. They're great maps for navigation. If you ever see anything that says conformal maps preserve shape, I would like you to keep in the back of your mind that yes, they do preserve shape for infinitely small regions. It's that last part that people often drop off. And when they're like, oh no, conformal projections, they totally preserve shape, so they're great, so people can recognize shapes really easily. My response to that, feel free to use this. If conformal maps preserved shape, wouldn't they all look the same? And then you get this look returned to you that's like, huh. That's a good question, because they don't all look the same. So those infinitely small shapes. Equal area projections. Equal area projections are probably the one that you'll use the most in thematic cartography. So for most kind of general purpose map making, they're just going to make it so that relative land areas or relative areas across your map are equivalent. Equidistant projections, which will preserve distance from 1 or 2 specific locations on the map. Don't let anybody try and convince you that an equidistant projection will let you take measurements between any 2 pairs of locations. You really have to specify the specific location where the values are going to be correct. And then you've got compromise projections, like a Robinson projection, and those are not equal area, they are not conformal, but they look kind of pretty. So, National Geographic e-maps, we'll just make that our last category. I'm not going to go a whole lot into map projections, but I do have some resources that I can recommend to you. The University Consortium on Geographic Information Science has a body of knowledge, and there's a fabulously well-written map projection one that I wrote last year There's this Map Projections Essentials from a company called Mathematics. It's written by a guy named Dan Strebe. Some of you who go to Kugos may have encountered Dan at some point in time, but he's a senior engineer, I guess a staff engineer out at Tableau, and is probably the world's leading living map projection expert. I think the Wikipedia entry is halfway decent. I know that Dan has also written a lot of it. And something that is not specific to just projections, but where I was trying to explain a lot of the, how can you think about projections and coordinate systems for a general audience? I wrote a blog post related to projecting data for use in Tableau software, but I think there'll be some general purpose topics that might be useful if you're curious. So why do you care? Have any of you guys seen this example? I didn't update. I actually have some examples similar to this from this year because people keep doing the same wrong things. So this is from The Economist, trusted news source. Graphics department needed to make a map for a story. The map looks very nice. They were given some distances on how far missiles could travel. And everybody knows what's the shortest distance between 2 points. It's a straight line. And if you draw a straight line from a point, you put your pencil in the middle and you got your other pencil on a string, what do you get? You get a nice circle. So all I have to do is figure out what is the distance, put my pencil down, draw my circle, and it's magic, right? So until they printed the correction, because what happened is the base map looks really good, but it's not an equidistant projection. So if you actually want real distances, you need to use an equidistant projection to calculate them. You don't have to display the results on an equidistant projection, but you need to do the calculations in the right projection. Let this be a lesson to you. One of my favorite map projection problems. This is one of those totally pernicious fungus of map projection problems. You cannot get away from this. Latitude and longitude. What is latitude and longitude? Somebody give me a quick definition. What is latitude and longitude? Angles. So we've got angles away from the equator. We've got angles away from the prime meridian. Latitude and longitude are totally latitude and longitude, right? So we've got this datum problem. You guys have been doing a lot of work in WGS 84, also known as our favorite 4326. And that's the World Geodetic Survey of 1984. And that has one definition of the Earth, of the shape of the Earth, and latitude and longitude are measured in angles using that model of the Earth. There are lots and lots of datums. Most online systems are going to assume that your latitude and longitude data is 4326. You may get data sets where the projection and the datum are not defined. It may not really be 4326. And then you get problems like this. Exactly the same data set, same latitude and longitude columns, drag them into the map, and all of a sudden we've got all this Redfin sales data for all of the houseboats. If you were zoomed out to the city of Seattle, you wouldn't have noticed this happened because the shifts can be relatively small. It can be like a 30-meter shift or something. What this is a data set in the North American datum of 1927. Which is a still fairly common datum to get US data in. And then the other one is a data set that actually came in either North American datum of 1983 or WGS 84, I don't remember which one. In North America, they're roughly equivalent. But if the coordinate system is not defined, if the datum is not defined, all the software sees is latitude value, longitude value, drop it on the map in WGS 84. And that's going to put your points in the wrong place. What happens when you do analysis with points that are in the wrong place? Your analyses are all wrong. And then you use that data for some other analyses, which is also wrong. And then you use that for some other analyses, which is yet still wrong. But it's really hard to pull out this sort of problem unless you really zoom in and dig into your data set and make sure that you understand what the coordinate reference system is. You could have some interesting analytic result problems. So I love heat maps. Everybody loves heat maps, right? Yeah. Heat maps and Hex Bins, they're awesome. So this is using the Google Heat Map API. And I took a data set. Dan Strebe and I manufactured this data set. And we're like, hey, let's check out heat maps. So we made a hotspot. Cool. We moved the data. We made some hotspots. Cool. Which is the hotter location? You guys probably know where this is going, right? These are exactly the same data set. Visually, what kind of pattern are people seeing? Let's say this is like clusters of, these are disease outbreaks. Oh, you know, if we focus our resources down by the equator, we just have to target one area. But if we focus our resources on that area in the northern hemisphere, we've got like 5 distinct hotspots that we have to like divide and conquer. No, you don't. Map projections. Web Mercator just stretches everything out up near the poles. So if you do analyses in this way, you're going to get answers that are probably misleading. Unless you read the documentation on the API, which, you know, I do for fun at night, you know, have a cup of tea and read some API documentation. It's really awesome. And you find out that it's calculated in pixel distance, not ground distance. Pixel distance is not the most awesome way to do your analyses. Pixel, not the same as like a foot on the ground. So because a lot of the work that you do may end up being put onto web maps, you're probably going to be dealing with this map projection, Web Mercator, 3857, I believe, if you want the EPSG code. You'll start to memorize them. Distances and areas are going to be distorted. If you're just talking about visual analysis, the high latitude areas are going to be overemphasized. If you're actually doing analyses, any of your spatial analyses done on the Web Mercator plane are going to be wrong. Unless you're working with a really, really small region, never do your analyses in this particular coordinate system. If the API is allowing you to do the analyses in that coordinate system, read the documentation carefully to find out if it's reprojecting your data first, then doing the calculation and giving you the result. Google does some cool stuff. Like if you take measurements, it will often give you, here's the straight line, and then also draw the great circle for you. And it will give you that great circle measurement. But it's worth checking to make sure that it's really giving you the right measurements whenever you're doing analyses in these environments. And just because I knew I was probably going to go over time anyway, and I think I still have like a nanosecond since we started a few minutes late. I want to give a quick note about my favorite map type with a big projection problem, because hex bins are cool. I saw hex bins in at least one project. Somebody was looking at some hex bin data. And I wanted to tell you about the big gotcha with this. So this is two sets. This is exactly the same data. I've just done color encoding on one, so darker hex bins are more stuff and lighter hex bins are less stuff. The color scheme is actually the same in the second map. I've just size encoded as well, so it emphasizes a little bit more that as we get up near the poles, we have fewer points in each of those hex bins. This is a fairly evenly distributed data set across the entire spherical world. What's happening with the binning? What's happening with the binning is, as we get closer to the poles in Web Mercator, distances get stretched, the bins get stretched, but they're actually covering a smaller and smaller ground area. Turns out when you have really small bins, not many points fall inside them. So it looks like visually we have this lower count or a lower density of values in the poles, even though the distribution is almost exactly even across the entire area. Why that happens? Because oftentimes when you use these built-in hex binning functions, they are going to define the edges of the hexagon based on the coordinate system units. So if you're working in Web Mercator, they may be drawn using Web Mercator meters. Or people try and get really, really smart, and they define the spatial bins with equal units of latitude and longitude. Because a degree is a degree, totally. And it ends up giving you bins that look kind of like this, which they are not visually the same area, nor are they geographically the same area. So you're providing a visually wrong map on top of bad data. People really do this. So this is an example from the Mapbox blog using the turf JavaScript library. If you look at these bins carefully, you're going to see as you get closer to the Canadian border, the bins actually start stretching out. They start getting taller. So they're defining the size of these bins in degrees of latitude and longitude, as opposed to in meters or kilometers or something that would be useful on the sphere. So I love hex bins, and I'm not going to stop you from making them because I think that they're really cool. But I will tell you that you probably want to think about how much distortion you can handle when you're creating these bins. The point of this graphic is not to understand the magic of what I just wrote down there about this allowable inflation factor, because I will give you a reference where you can look that up for free, and it will let you give you a really easy calculation of, if this is my latitude of my data set, here is how big of an area I can bin my data in before distortion starts to be a significant enough problem that my analyses are probably going to be flawed. So we've made it easy for you, and you can make rainbowy graphics like this, should you want. Let me see if this is going to play. Since I'm talking about hex bins, I just want to point out one other problem. It's the modifiable area unit problem. So where you put your bins is going to change the pattern that you get. So watch as is this actually showing? Yeah, okay, so it is kind of moving. It moves way better on my screen. The point is, if you were watching this animation live, as the grid is moving over the points, hot spots come and go. The point is, where you place bins that you use in your analyses and the size of the bins can drastically alter the visual result that you get. And here is the more than you probably wanted to know about it in journal article form, which you can get for free from the Research Tableau website. Just look for my name and the paper is linked. But I wrote a paper with Dan Strebe and Mike Finn, who was at the US Geological Survey. He just retired. But we wrote a paper that I think I think it's the best title of any paper I've ever written, Shapes on a Plane. And I was told by the journal editor that this would not be an appropriate cover graphic for the journal. And I was kind of sad about that until he pointed out that he thought it was just kind of like too busy and stuff. And I was like, it's not because of the copyright issues. I thought it would be a copyright issue problem. And he's like, what copyright issues? It's like, let me tell you about snakes on a plane. So we talk about a lot of the binning problems, focusing on what are the issues with map projections. And so this will have some information that'll be relevant for any kind of spatial binning that you want to do with your data. And since I was trying to keep it, close to within my half hour, I'll go ahead and stop, because I think that's probably enough examples for you to be dangerous. If you do have mapping questions or you want to talk about some of the things you're doing, I'll probably be here for about another hour before I have to go walk back to my office. But I'm totally happy to answer questions over email. Anytime you want to have a little cartographic discussion, let me know. Thank you.